Alright, in this lesson we're discussing continuity. The functions that we have explained thus far have been continuous functions. We say that they are continuous because there are no breaks or holes in the graphs. If a function is not continuous, it is discontinuous. And there are three basic types of discontinuity. You could either have an infinite discontinuity, meaning there is some type of asymptote on the graph, or f of x approaches infinity. You can have a jump discontinuity, where there's a break in the graph. And then you can also have a point discontinuity, where there is a hole in the graph. Now, if that hole can be filled by factoring, then we say that this type of point discontinuity is removable discontinuity. So if a break can be avoided by factoring, like I said, we say that it's a removable discontinuity. For example, if you have this function and you factor the numerator, you see that the x minus 4's cancel, leaving you with x minus 1. Therefore, we say this function has removable discontinuity at x equals 4. All right, first example. We want to see if this function is continuous at x equals -2. First thing we should do is factor the numerator. When we factor the numerator, we'll see that x plus 2 cancels, leaving us with negative x minus 4. So yes, the function is continuous at x equals -2 because there's removable discontinuity at x equals -2. Next example, we have a piecewise function, and the function is not continuous because we have one graph for the x values less than 2. We have another graph for the x values that are greater than or equal to 2. So there's jump discontinuity at x equals 2. First thing we want to do for this example is factor the denominator. Once we factor the denominator, we see that the x plus 2's will cancel, leaving us with 1 over x minus 1. So although we were able to remove one whole, we were not able to, x still cannot equal 1. All right, so there's going to be an asymptote at x equals 1. So that it is not going to be continuous. So we have removable discontinuity at x equals -2. And then we have infinite discontinuity at x equals 1 since there's an asymptote at x equals 1. All right, next example. We want to describe the interval of continuity. So we know that x, the denominator, cannot equal 0. So if we set the expression in the denominator equal to 0, we see that x cannot equal 2. There's an asymptote at x equals 2, so we say there's infinite discontinuity at x equals 2. Therefore, the interval of continuity will go from -infinity to 2, not including the 2, and then again from 2 to positive infinity. And the last example, we have another piecewise function. And we see that there is jump discontinuity at x equals -4. There's a break. Therefore, the interval of continuity goes from -infinity to -4. And we use a square bracket at -4 because the function is defined in that top function, 2x plus 5. It is defined at that function whenever x equals 4. And then it's also continuous from -4 to positive infinity.